Much. And first of all, I'm very honored to be probably one of the youngest people to attest to Rusty's legacy. And so when did I actually meet him the first time? That was about 15 years ago when we, after a 10-year break, rebooted MPI 2 as MPI 2.1. And I remember distinctly, I was this very young student, very pushy, as some of you. and I walked in the room and I was ready to tell everybody that they had no idea what they were doing, and I have the solution for everything in hand with my non-blocking collectives, which was the topic of my PhD. And I gave my speech, and it didn't go too well in the first meeting. Or may have been the second. And then Rusty walked up to me and told me, well, this is not how we work here. Then he explained me how this is going. This is exactly what Bill said yesterday, in this wonderful setting. And from that, I completely changed my way to approach humans, other humans, let's say. So that's my little story, how I met him first. And I did bring a poem. So let me read this poem. Rusty Lusk, a name we know, a researcher who helped MPI grow. At Argonne National Laboratory, his contributions were legendary. He worked on MPI 2 and MPI 3 and made parallel computing history. His work on MPI I/O was key, and he helped make parallel I/O a reality. He was a mentor to many, and his work inspired plenty. His legacy will live on in the work of those he shone upon. May his memory be a blessing and his work continue progressing. And thanks for the applause, but I have to tell you, I did not write that poem. Not at all. I asked an AI to write that poem, and some of you said ChatGPT. No, it's not ChatGPT. It's Bing, but it's the same base model. And actually, there's a very direct connection between Rusty and that model, and I'm going to talk about that a little bit more. So to paraphrase Satoshi's statement, he may have saved millions of lives. I would claim that what Rusty has done and our community has managed to push forward will impact billions of lives in a completely new way of working in the future, such that such poems come out of a 2-line prompt. I just told the thing, write me a nice poem about Rusty Lusk. That thing went to the internet, looked him up, made some little mistakes. Some of you will see mistakes. There are also typos in there, but those can be fixed. So that's going to be the story. But actually, there's one thing I have to say. Rusty started at Argonne in 1980. Before I was even planned. So he probably looked like this, or close to this. And it's also funny, I did not understand for the longest time this discrepancy between his first name and his nickname. Well, that's a black and white picture, but we share some commonality here, and I did not get it. I was really absolutely not getting it. And then, of course, he moved on with some people. Some people find yourself here, Jack and Paul, and defined the future of parallel computing, which is what we are talking about now. But one distinct thing about Rusty, I really have to say, he was always the guy, and you see it on these pictures, and there are more coming. What is the commonality on these pictures? He's always smiling. Exactly. That was when I walked into the room in the MPI forum. He was the guy who had this bright smile on his face pretty much always. And I did not actually find a single picture where he was not smiling like this. So it's very easy to find all these smiling pictures. But what I'm going to talk about is really the MPI standard. And Jack attests to this, that this is what Rusty considers one of his major achievements. And I can also attest to this. But I have only overlapped very little with Rusty in that late time. So I'm going to tell you how he really helped me develop and move forward in a couple of minutes, and then I will go to really the impact. Well, what was my personal journey with MPI? So I actually grew up in East Germany, red hair communist. I fit right in, and actually my career, why I'm standing here, was determined by the GDR's Secret Service, which is very well known. I mean, some of you may have seen The Life of the Others. It's a very well organized system. And was his logo. And what's the connection between me standing here and the GDR Secret Service? Well, I was a networking student. I was studying networking, intranetworking. And my professor disappeared from one day to another. And nobody knew where he got. I still have his books at home. He just never came to claim them. Reasoning behind this was he apparently, I heard he was a high officer in the Secret Service and had to disappear. Well, I don't know. But I was at this university in East Germany, a very small place in the poor region of the country, The only thing to be seen there is a big Marx head. That's the largest Karl Marx head on the planet. Yeah. But the real thing from our perspective, what they had there is Chempi, Chemnitz MPI. Who has heard about this? Nobody. Exactly. We did, exactly. It was how I started. Because after that professor disappeared, I had to find a new advisor, obviously, because it was in the middle of my master's thesis. And so I moved to work on Chempi, which is based on MPitch. So I worked on Rusty's builds and everybody's code. I wrote a diploma thesis, which was called at the time, on the barrier operation, which they even gave me an award for because apparently it was really good. Later I realized, oh, nobody is actually using barrier in practice. That was a little bit sad, so I was really proud of this. Nobody was using it. And then I was getting involved with Open MPI, and eventually Jeff Squires told me to come to the US. When I joined Indiana University, thank you, Michael, for heading that place while I was there and got my PhD. Then 2 weeks before I arrived, Jeff decided to disappear to industry, so I worked with Andrew, who many of you know, and this is how I met Rusty. So Andrew enabled me to really join the MPI forum and then interact more with Rusty. So the one thing I also distinctly remember is reading this book that was quoted yesterday, and it's a wonderful book. Everything I learned about MPI2 was there, and it's these three people we all know. And I'm really honored that I was allowed to join that club 15 years later to publish a new book using advanced MPI. And now, going 9 years further forward, we are at today. So now, what is going on today? So what is the big news in the very recent past that we have seen? Well, it's this AI revolution, and there are news coming on a weekly basis. So looking at the success of ChatGPT just in January, it would pass the bar exam. Late January, we would basically get an MBA, would pass the medical licensing exam. Now I'm scared. January 19. So now it would actually make more money than I do if it would apply at Google. So the question I was really asking is, what is left for us as humans to do here in this world? And I went and tried to understand what's left for humans once the AI is coming. And I went back to a paper in 2016. So in 2016, the closest thing to a human was not an AI like today. 2016, the closest thing to a human was a chimpanzee. And then they studied what makes a difference between chimpanzees and humans. And really the one distinctive thing that is the difference is that humans have a theory of mind. This is what makes humanity, if you think about it. I have some kind of mental model of what's going on in your head. You're probably thinking, oh my God, what is that guy telling me? And I, through that mental model of you, can connect to you. This enables development. This enables communication. This enables how we achieve big things together as a species. And this is very much what I'm hearing here, Rusty's core skill. Communication, mediating, really working together. And well, the problem is these AI models are going to take that from us as well. And I did these tests myself, so it has been shown that these models have a theory of mind, that they can actually reason about what other humans may be thinking. And I did these tests myself, so basically like complex tests where you look at X did something to Y gave Z flowers, and really complex social settings. And I would have lost to the AI model. But well, I did learn something from Rusty. He would certainly gain that. The other thing that is actually reasonably interesting here is that just a couple of weeks ago, OpenAI used that model to make it work on some tests. So this is a series of tests, I don't know, it's probably 15 or something like this. These are written tests for exams, like GRE writing, biology, verbal exam, or English literature, or something like this. So written tests. They just let the model take these tests and mixed it to humans in a blind trial. So it was together with humans taking the test. And what we see here is the percentile where the model lies in comparison of the stack with the humans. And what the astonishing thing we are seeing here that in more than 50% of the tests, the model is better than the average human, than the 50th percentile of the human. So that changed my view on what happened in the recent past, very recent past, with these developments. So, but what's the connection to MPI? He's telling me about AI, and there's always these annoying people talking about AI all the time. It's going to change the world, blah, blah, blah. Well, I mean, by the way, 30th anniversary is very close of MPI. So happy 30th birthday. Another picture generated by, by an AI. And we see Rusty here being very happy. And by the way, thank you, Bridget, for hosting us at the 25 years MPI meeting. That was wonderful. So I also got to see Rusty's home and Rusty there. It was absolutely amazing. But now let's ask where this AI comes from. So let's ask some of the godfathers of AI. There was as probably many of you know, they received the Turing Award, 3 people, Bengio, Hinton, and LeCun. And there was a big lecture in 2018 where Geoffrey Hinton gave the background on how this came into fruition. And I want to quote 2 things here. Really, the deciding factor for this AI revolution, essentially, was the increase in compute power. Furthermore, I think a lot of credit for deep learning goes to the people who made the computers go fast. Well, that resonates with us, isn't it? That's really a quote. You find the minutes in the recording there. You can look this up. And who is better to be asked about this, how to make computers go fast? Well, it's Jack, of course, because we did go towards what the future of AI is back in the 80s, 70s, and of course the whole crew, Rusty and everybody involved, and make this really fast. Right? So when I joined Microsoft in the sabbatical in 2019, there was one interesting move that I distinctly remember as well. So Greg Brockman, the CTO of OpenAI at the time, and still, he made this statement: we think the most benefit will go to whoever has the biggest computer. And he was right. He was right. That was very much what happened. And Rusty was in the business of building big computers like we all are. Right? So what happened since then? Well, since then, many of the AI systems are supercomputers. Industry, for I believe the first time in history, is deploying computers that are comparable in scale to big government machines. Right? Meta deploys a supercomputer. Tesla builds their own supercomputer completely from scratch. They built their own chips, they built their own network. Just that Elon Musk announced last week that they're buying $250 million worth of GPUs. So maybe it is actually repeating the HPC tradition of some failed approaches do not necessarily come to fruition. So you could see that as one of those startups that may or may not really have succeeded. Google has their own supercomputer, a little bit more successful. They're actually deploying it at scale, the TPU system. And then while I was there, Microsoft pledged $1 billion. And that's quite a bit of money if you say, I'm now building a supercomputer for $1 billion to achieve artificial intelligence. They even made a comic about it. The publicly available information is 10,000 GPUs. Now the question is, how does this work technically? Rajiv asked me very distinctly to give a technical talk. So I apologize. I had to pay a little bit more of a tribute. Let me now get to the technical talk. How these models actually work in detail? That can write poems, that can generate images, that can do all kinds of stuff that you would usually think a human is required to do. Well, it's actually very simple. So we take a text from the internet, like this one, and in this text, we of course have the text, and we remove a word. It's very simplified here in this model, but this is really how it works. We remove a word, then we run it through a function that is implemented by a transformer architecture. That's a deep neural network, and I'm simplifying things here again, but it's actually pretty close to how it works. And then this function gives me a probability distribution here of all possible words. So this is, in the English language, this is a vector of dimension 30,000. I'm just putting some examples here. And then it guesses which probability the right word should be. So it's trying to guess the word we removed. Of course, most of you can totally guess what was removed. And we, of course, since we removed it, we know what we removed. So what we now do is we see, oh, great, this is the right solution. So what we now do is we feed this backwards. We update the weights in the model. There are lots of parameters in the model to be, in the next iteration, closer to the real world. And we do this hundreds of thousands of times. This is where the HPC comes in. So now let's look a bit at the scale. So this model that many of us are using, like the first version of ChatGPT, was trained on 300 billion tokens. 500 billion tokens. So these are words. And soon we are going to train on the whole internet. And the internet is large. Actually, what I'm saying now, every word I'm speaking now, I'm 100% convinced will go through at least a dozen different deep neural networks. Like the moment you upload it on Google, the machines will learn from what I'm saying right now, everybody has said. It's in your machine. Yes, exactly, your biological brain. But I believe that you're not running at gigahertz. We shall see. So then this model itself is pretty complex, actually. This has about 700 gigabyte of FP32 weights. So these models are large these days. And this is, again, where supercomputing comes in, where HPC comes in, where MPI comes in. And it takes weeks to train, again, a supercomputing task. So, and I'm so glad I can finally say this. OpenAI publicly admitted that they're using MPI to train these models just last week. So I knew it a little bit longer, but now there's a blog post that I can point at and say, hey. So they're actually running for all the training of these models, saying it here, our biggest jobs, and of course the biggest jobs are how you train these things, are running MPI. So really the thing that Rusty helped build. So this is absolutely amazing. And this is how things, I mean, the work that many have done is actually having an impact on society at large, as we will see in the very, very, very near future. So now getting a little bit more into details, technical details. I'm still here. I know the technical talk is coming, Rajiv. Technical details. What is the problem in these calculations? Data movement is a problem. And now I don't have enough time to tell you about why exactly data movement is a problem. Believe me, I know it. I could tell you. It would just take another hour. You can watch that online if you want, if you're really interested in the technical details. Sorry. But I'll get to the point in the network, because MPI is all about the network. I think this is a very good opportunity to give my favorite Rusty quote here. So again, linking back to my first interaction with him, this is my favorite quote. You have to have strong opinions, but you better hold them weakly. This is what I learned. I have very strong opinions, but you can still argue me out of ways now. And I always think about that quote when I'm going there. So now let's get a little bit more technical. These deep learning models, how do we actually train them with MPI? What role does MPI really play there? Well, as I mentioned, we have a lot of text, literally gigabytes, hundreds of gigabytes to terabytes of text. And we run those in so-called data parallelism through basically different copies of the model. So here we have the 3 different copies, like a green, a blue, and a yellowish copy of the full model. Okay, so we run the first page through the first model, the second page through the second, and so on. Of course, we have to make sure that these copies of the model somehow synchronize. Right? This is where it's coming in. We want to train one model at the end and not 3 distinct models. So we have to exchange the weights every now and then and make sure they synchronize. I'll get to the details later. But now the problem with this is that I mentioned each of these models is 700 gigabyte. Well, I don't have an accelerator with 700 gigabyte of memory, so what I need to do is I need to cut the model itself, the so-called pipeline parallelism, where I'm taking the first layer of the model, put it on some accelerator, so this guy, the second layer of the model, I put it in some, and the third layer. As I mentioned, GPT-3 has 96 layers, so if you want to be very precise, so there will be 96 accelerators in this dimension, and then it actually fits. If you divide 700 gigabyte by 96, then you're down to like 10-ish gigabyte with all the overhead, so it fits your GPU. But no, it doesn't actually get faster if you do pipeline parallelism, because it still goes to every accelerator. It actually gets slightly slower. It just enables you to do this computation. And now you realize that ChatGPT is not super slow. It is kind of slow, but it's not super slow. So how do we make this faster? This is the third level of parallelism. So remember, we already employ 3 by 3 accelerators here. We already have 9 accelerators in this little view graph. And I'm now adding another layer of accelerators, where I'm adding 3 more, where I'm basically saying, well, now we cut each of these operators into smaller pieces. And this is where the typical HPC calculation would be used. Okay, so let me talk a little bit about data parallelism. So data parallelism has a very interesting history. Did I mention that I have strong opinions? Well, I walked into the room with all these machine learning people a while ago, a long while ago, that's not nearly 7 years ago. And I, of course, remembered Rusty's statement, yeah, be careful, be careful. But they were doing this really silly thing, in my view. I mean, incredibly silly. They even gave a keynote on this. And I was like, oh my God, what are you doing? So let me tell you what they're doing. So they had all these MPI processes, essentially. Of course, they didn't use MPI at the time because they didn't know better. They were using some kind of TCP communication thing that was a total disaster. And then they had these servers sitting here. So we had N ranks and M servers. And basically in order to synchronize, these are called parameter servers. If you Google for the old literature, you will still find those. But what they did was every rank was sending all the weights to these, or all the gradients, depending on what you were summing, to these parameter servers, and you did this and this and this, and then you were distributing this in kind of a silly way. And of course, like HPC people, we know if you scale N to large, I mean, to quote Rusty, MPI on 10 million processes, why not? There's a talk of him on the web that has that title. Why not? Well, if you make this 10 million and you send to a single server, that's not a good idea. We all know this. And basically, if you want to mathematize this, Rusty was a big fan of performance modeling, and was a big fan of performance modeling, so you'll see some equations here. You can see those. I don't want to explain those. This is probably boring. So this is pretty sad for machine learning. This model would have not succeeded to train the models that we're using today. Like, no way. No way. Okay, so what did they do in this community? Well, they reinvented rings. They reinvented ring communication, which is something that we knew forever. So they came and reinvented this wonderful ring algorithm where you always send to your neighbor, and you do this with various blocks, and you keep going, and you do n iterations of this. Then you realize, well, if you do this, it was n times n before, and now it's n times n. So it's actually much better. And if the second one looks kind of good, but unfortunately they're hiding a factor of 2 here, so that also in the asymptotic notation doesn't work too well. So in fact, this is slower. For some settings of parameters. And then I was wondering, why do you do this? Well, they do it. There's this very interesting article here, learning at scale. But if I see Mark look funny because it's like at scale, if you scale this to many processes, this is not going to work well, right? Because it's an n square message algorithm, not a good idea. So somehow there's a problem was a problem in the community. So what happened then? Well, what happened then is they finally got to look up what other people have been doing for the last 3 decades, and realized, well, maybe that is not a new problem. Maybe summing numbers on computers has been covered by somebody who has been building computers. And then they looked it up, and then they realized, oh, it's actually this reduce scatter plus all gather algorithm that's quite nice. It could be quite nice. And so how does it work? It's a bit more complicated, and I, again, don't want to explain the real details here, but there's a skip communication, essentially, with kind of a ring-lang scheme. So you get to n log n messages and log n plus s time, which is actually optimal. So, and this algorithm, computer's happy. By the way, these are also automatically generated by the model. Pretty much all pictures on my slides are, because I got to do a copyright fight at some point, so this is the easiest way to avoid this. This was published in 2005. Right? It took them nearly 13 years to look up this paper to drive the billion-dollar industry. So this is about siloing. I see Bill laughing. We always talk about siloing, and I put it on my flag to connect these two communities. I want to bring our goodies into their business, but also their business into their goodies into our business. We will see how that works. So, well, it's not all exactly how we envisioned it in the past. Actually, there's one big thing you can do in deep learning models that we have not really anticipated. And one of these things is that our brains are incredibly unreliable. Like my neurons only work about 70% of the time right. I'm still able to speak to you and it still works well, so that's not bad. In fact, for deep learning models, it's very similar. You can actually drop a lot of content. There are models where in the summation, you can drop 99.9% of the values and it still works well. Oh, great. Did I mention that communication, I mean, the communication is the bottleneck and we can just drop 99.9% of the values? Well, there's some tricks to it. We can talk about this offline, how to actually recover this. There are lots of proofs you can run. There's lots of empirical evidence here. So this is the training curve for a deep learning model. If you only communicate 0.025% of the largest gradient values, and basically it's the same. You don't see any difference to the baseline where you communicate 100%. So that's a new thing that we should be considering as an MPI community. How could we address those things? Because what's now happening is that every rank in our system, every process in our system will drop a lot of information and then communicate only a subset of the information that is important. So very data-driven. MPI used to be less data-driven, I would say, in the early days. And Rusty was actually, with his ADLB, pushing towards more data-driven. Right? So it's a different dimension that I'm talking about, but it's a very similar idea. So here, basically a small visualization. If now everybody sums up a sparse vector, these vectors are going to fill up. So there are 4 MPI processes, and they're basically, if I'm adding 2 non-zeros, I get here all in black is non-zero, white is 0. If I'm adding 2 non-zeros, I will of course get a non-zero. If I add a 0 to a non-zero, I will get a non-zero, and so on. So there's some filling going on, and we could talk about how great this is, but I don't want to spend too much time on this. But actually, this is a fundamental principle in large-scale AI, sparsity. So we can actually use these models and we can remove a lot of the content. So this is just an illustration of a deep learning model. We can remove many of the features, like you can read this, even though it's missing about 30% of the letters. And we can do the same thing in the deep neural network. So we can remove up to 95% of the weights to go forward. That's just as a side note. So now we can go a little bit more into details, but I just want to flash these things and go into pipeline parallelism. Pipeline parallelism is quite complex, and I'm running out of time here because the beginning took longer than I thought. So let me just skip that part, the pipeline parallelism. We can talk about this offline if you're really interested, but it's also a quite nice thing that we basically do on top of MPI, this time with MPI send receive. Before it was all reduced. This is MPI send receive that we are now using, and we achieve very high performance on a real supercomputer, of course speeding up overall comparative systems. If you now look at these numbers, like 2x speed up, and remember it's $1 billion industry, so that is actually quite a lot. A factor 2x may sound pretty small, but if it's $1 billion industry, it's a lot. Then tensor parallelism is basically the same thing, so let me just skip this here as well. And now I want to just summarize this nice model of parallelism, so how we use MPI and how we use communication in deep learning. And this is very fundamental, I think. This is all the models that we use today have exactly that three-dimensional view. So we can basically align these three forms of parallelism in a way that we have the data parallelism going in this D dimension here, which is basically, you can phrase it always as a nearest neighbor communication. So the green one communicates with the yellow one communicates with the blue one if you use the ring algorithm. The pipeline parallelism is kind of the same thing, but it goes from left to right. It's the same model, just goes from left to right in a single copy of this model. The operator parallelism is again the same thing. It goes from top to bottom. This is an all reduce, this is an all reduce, this is an MPI send. This is basically summarizing how to parallelize deep learning at large scale. And now, if we combine these three, what is the topology that results? Is anybody paying attention? So this is a one-dimensional ring. This is a one-dimensional kind of ring. This is also a one-dimensional ring. Putting the three together is a three-dimensional torus. And that is, yeah, Larry, you got it. And this is exactly what one of the main insights could be here. And if you now think this to an end, you could actually build a machine. Because, well, did I mention that communication is the most expensive thing? So MPI is going to be the limiting factor in this model. So we could now build a machine that takes advantage of this insight that sits somewhere between a global topology, which is extremely expensive, and the very limited topology, a two-dimensional torus, which Google has been using in the first generations, which is extremely limited. So expensive, cheap and limited, expensive and super flexible. So you can now invent something in the middle that we call Hemming mesh, and I invented that with my colleagues at Microsoft, which is basically somewhere in between. The nice thing is it's about 15 times cheaper and blah, blah, blah. But really, what is now happening based on this insight is that you can build it in practice. Of course, not Microsoft built it, because all the cool stuff is invented in Microsoft, but Google then builds it, and in this particular case. So they actually, just last week, released that the TPU v3 is basically that exact topology based on the insight that you have three different directions of communication. So with that, I would like to conclude my little homage. So it was really great to know Rusty, and the guy who was always smiling. That's what I remember. Supercomputers, the supercomputing and MPI has really driven the development of large-scale AI, and many of us have contributed to this. You can learn something about how these models work. They're relatively simple, and then you can actually build specific systems for these models. And I want to also pledge to the community that we need to be open-minded. Like as Rusty would be saying, we can have a strong opinion, but we need to hold it weakly, which means that we must be very careful to not be ingrained too much in what our thinking is, but embrace the new ways of thinking. For example, the sparsity I was mentioning. For example, low precision data types that are now coming through AI systems. And with that, I would like to finish my talk and see if anybody has questions. Thank you. Or comments. Oh, come on, Ian.
Did you have a question, or I have?
So, Torsten, your last statement about network policy and so forth. So given that the economics of building these machines will shift towards benefiting AI and HPC, there are a lot of talk about HPC leveraging the AI industry rather than beating it. But we don't know what's going to happen, but assuming there needs to be lots of leverage. And what you mentioned is a torus network, or some sort of torus network would be more beneficial. And by the way, I know this one very big giant machine which uses a torus network. And so given that, do you think the community will move towards not optimize, having a low hop, low latency network to moving towards torus networks? Because A, it'll benefit AI, and B, a lot of the weak scaling problems, once they get to certain, unless there was a talk about strong scaling regime, which I think was a wonderful talk yesterday. But given that torus network has been successful in multiple machines like BlueGene or Fugaku, do you think the industry will move towards that?
That is an excellent question. I'm torn on this. I would not want to give a definite answer whether industry is going to move towards torus-like networks or not, because there are some problems with torus-like networks. The allocation is very complicated. And so we basically solved many of these allocation problems if you only have a subtorus that you're basically disconnecting the ends somehow. I mean, they would need to route through a long path to get to the other side. We solved this with this Hamming mesh topology, or with the Google TPU v4 topology, by connecting those fully. So you get more flexible this way. And now the question is, what's the trade-off between flexibility and well, money, right? And I would say intuitively yes, because it's the right direction. I hope I communicated that why. But they're always, as we learned yesterday, I mean, yesterday, thank you so much for giving all these eye-opening talks. It's not always the right technology that wins, It's a very complicated situation between like investments and startups and people that will guide technology at the end. So I would have a very hard time making a prediction what's going to happen. I think I know what I believe the right technology is, but that may not be what's going to happen. I've seen too many people disappointed. Yeah. Yeah.
You asked me to ask a question.
Thank you.
So you talked at the end about various ways in which you're in a very controlled manner. One is reducing precision and things and discarding data. The next step could be to embrace sort of greatly reduce reliability in your hardware and allow for accidental deletion of things and reducing costs in that way. Do you think that is going to happen, and what will it mean for MPI? Here we go.
Oh my God. MPI and fault tolerance. That's a tough one. First, let me address the question on the hardware. So I believe that we can totally run these workloads on unreliable hardware. At the end, my brain is a super unreliable hardware that this runs on. It's very astonishing that this works. It's mainly working on averages. It's also interesting that the differentiation of our pulses in the brain can differentiate 24 voltage levels at a very low reliability. So that's 4.3 bits or something like this. So we're basically operating on 4.3 bit numbers, if you think about this, if you model ourselves as a binary system. So yes, you can drop a lot. Like, there are these stories from people having like shot away half the brain and they still function reasonably well. I think we can translate this to hardware as long as it's not control flow. Somehow the brain doesn't have explicit control flow. It's not a von Neumann machine. It's like wired, and that's kind of the control, but we don't really understand how it works. In machines, we have explicit control flow. If you disturb this, the thing will just crash. But if you just disturb the values, that's all fine. And the problem with this explicit control flow is exactly now carrying over to MPI, what we were discussing. What the heck happens if one rank just disappears? Like we don't even know a concrete, like a consistent state. But somehow I think we have to give up this view of the consistent state. I think there's no consistent state. If things keep failing, there is always kind of an average state of an average model, but we don't know how to reason about this algorithmically. We don't understand how to program systems this way yet. And I think that's something to look into. And how does this relate to MPI? Well, MPI would basically be the way to enable this on a real big system. Like we can do this in the small, we can do this on a single GPU, on a single CPU, but we would need to deal with concepts of MPI. And I really see MPI as a collection of concepts and a beautiful implementation. But these are separate. The concepts and the implementation are two very separate things. And these concepts that we need to figure out for unreliable large-scale computing, many people have tried it, by the way. I mean, Algeist and many have pushed these visions, and I think these are good directions to go into. I'm just not sure what the first step would be.
Torsten, I have a question. You mentioned there's 3 levels of parallelism. So my question is, this 3-level parallelism is all in the processor level, or could it be a accelerator level, or processor level, or I/O level? Do you have a different level of the parallelism?
That's a wonderful question. So the answer is no. Actually, these 3 levels you usually exploit at different heights of the stack. So for example, the data parallel level is, as you mentioned, an I/O problem. Rusty would have liked it because you have parallel I/O. You read from a lot of different sources data. Unfortunately, there's not a lot of data in text data, so it's not a real big compute problem. The data parallelism, again, this is distributed typically. The pipeline parallelism is forced upon you. You have to distribute because you don't fit it into your accelerator period, unless you have a Cerebras machine. But otherwise, you don't. Even there, you don't really fit it, exactly. I didn't want to make that comment, thank you. And the third dimension, the model or tensor parallelism, what some people call it, I call it operator parallelism, that is usually implemented as vectorization or as parallelism in the GPU, in a single GPU. The problem is, as you grow these models, and we've been seeing humongous growth, I mean, basically much of the benefit, as to emphasize it again, of these models comes from scaling them larger. This is a true HPC problem. This is really our community, scaling them up. And the interesting thing there is that at some point they don't fit a single GPU anymore, and then you have to jump the cliff to make it multi. Nobody wants to go multi-node for very tightly coupled things, but you have to. This is exactly the story of our life, right? As you scale up things, it's like, oh God, no, I fall off a cliff. So it really depends. Today, the models we are running at the scale of GPT-4 or GPT-3, they are all distributed in all 3 dimensions. They run on distributed systems because they would be too slow otherwise. So MPI plays a key role in all of these 3 dimensions. But if you go to smaller models like ResNet or something like this, then of course not. So it really depends on the size of your model. But thank you.
I have no idea how quick it is.
Oh my God, I'll be fast.
Whatever. So there's a lot of concern about the impact of AI on society. The question is, do you share those concerns, or do you have any concerns? And if so, what are they? Maybe restrict yourself to a few.
I'll give the very short answer. Yes, I share those concerns because I'm seeing internal models that are just, if you think the poem is cool, there's more coming. Okay, so we are not at the end of scaling these models, and it is getting scary. I mean, if you follow the recent news, oh, okay, I'm getting too long. Last week, look up AutoGPT, where they hook up these models to themselves to make planning and things, and then it gets humans. It gets very human. The models make plans. Interesting. So am I really afraid of this whole thing? Personally, I think this will just beat us eventually. The AI systems will be, at some point, smarter than the average human, which they probably already are, at least smarter than I am, because I wouldn't pass any of those tests. And eventually smarter than the collection of all humans, right? If we keep scaling like this, we have to see whether we do. So yeah, I'm not scared though. I think there are tools. It's like the calculator, and just don't hook them up to the real world, maybe. Autonomous, self-replicating robots, but then we can go into philosophy. So let's take this offline. Thank you very much.